today we are going to learn how to calculate momentum during collisions. Just like we said, we talked about impulse before and how when we have two things colliding, then it produces an impulse. Anytime one object shoves on the other, we get an impulse. And when, of course, two things hit each other, then the impulse on one object is equal but opposite to the impulse on the other one. So there are three basic ways that we can crash. One is elastically, one is inelastically, and the third is explosions. Elastic is like something that bounces. So what would be an example of an elastic collision? A ball. Okay, a ball and what's the ball colliding?
A face.
A ball and a face. Okay. I was thinking maybe one of our tennis players might say tennis ball and tennis racket. Oh yeah. So if a tennis ball and a tennis racket collide, then they bounce off of each other. That would work out nice. Bob would bounce off of a bowling pin. And so they're not going to stick together. So most of our sports involve things that are elastic collisions, but not all sports, because we also have inelastic collisions where they stick together. What sport would have that? Football. If you tackle properly, you grab them and hold on to them, and two objects become one object as you tackle them. Bad tackles are oftentimes elastic, where you come up and you smack a guy, but if he's got good balance, he just bounces to the side and keeps running. And that's not good. You got to wrap up and finish. That's what my college team has a problem with sometimes. It's like, finish that. Quit doing the elastic collision. Explosions, on the other hand, are like backwards crashes. If I was going one way and I had an equal amount of momentum going the other way and they smash into each other, they're going to just stop, right? And an explosion is that backwards. They can go and part of it goes flying and part of it goes flying. We should have equal momentum going the opposite direction. So we'll get into that in a little bit more detail. Another example of inelastic collision is also in football when you throw the ball to somebody. Because if you catch the ball, then the ball had some momentum and you had some momentum, and when you grab each other, then that would be more fun if I toss Bob at you, right?
Yes.
Here, and you catch.
How heavy is it?
16?
60 pounds?
Yeah.
Toss it, right?
Okay, now did you notice that Aaron moved when the ball hit him?
Yes.
Yeah. So, yeah. So there's, once the ball hit him, it moved him backwards a little bit. Now, it didn't move him back a lot because he's a lot heavier than Bob is, but you definitely want to be ready for that one. Okay, now, each of these three is going to have a separate formula, but our basic underlying concept is always the same, and that is that the total momentum in a collision is conserved. Physicists get very excited about things that are conserved because we can predict very accurately with them. We like that. So, two objects that are colliding, they again have to push each other with the same force, equal but opposite force, for the same time, so the impulse on both is the same. We talked about this last week. How if you're a little kid playing t-ball and you smack that t-ball with your bat, then the bat hits the ball just as long as the ball hits the bat, but in the opposite direction. So we have the same time, we have the same force, and so we have the same impulse. So the bat seems to slow down, the ball speeds up, so the ball gains some momentum, the bat lost some momentum. We end up having the total amount of momentum ends up being the same. So an impulse always causes a change in momentum, but one of them is going to seem to lose some momentum, the other one's going to gain some momentum, so the total overall momentum is still the same. We like this because it's reality and it actually lets us predict what should happen ahead of time. So our generic formula is P equals P prime. That little prime mark stands for after. So this says the momentum before the collision equals the momentum after the collision. So that little prime mark means after. So, yeah. So total momentum before equals total momentum afterwards, which means we can shift the momentum around, but the total is going to be constant. So that's kind of cool. explosions are the simplest one, so we'll handle those first. Before it goes boom, and after it goes boom, it should be the same. So after we explode something, it should just be 0 because before we pull the trigger, the boom didn't happen. So we've got that kind of action. So all pieces considering direction are going to cancel each other out. Now, if I'm tossing a hand grenade up in the air and it goes boom, then it's a little bit more complicated because we have a lot of pieces. But what happens if we have an explosion that only has 2 pieces in it? That would be mathematically easier, right? But is that realistic?
No.
Yes, it happens all the time.
Easter egg.
No, when you grab something and you pull the trigger, there's an explosion that happens. And a little piece comes out that we call the bullet, and it goes flying in one direction, and then the gun is going to fly in the other direction. Has anybody ever shot a gun or a rifle before?
Yes.
Yes, what happens to the gun?
Recoil.
Yeah, we have this recoil, and the momentum is the same. So if there's only 2 pieces, we say we had nothing beforehand, and afterwards these two have to add up to nothing, which means P1 is equal but opposite to P2. But then, of course, since P equals MV, P1 will turn into M1V1, and P2 will turn into M2V2. That would So here we have a beautiful video again. This is my oldest son, and he's shooting a rifle. So when you look at this rifle, when the bullet goes flying out one way, you'll notice the gun went the other way. So it keeps firing backward.
Did he get hit in the face?
No, he's smiling. Is he gonna smile if you smack him in the face? Now, what happens is there is a little bit of room here. There's some room in between where the scope is and where his eye is. That scope distance is actually a very important distance. And so it's really important, especially those of you who are smaller bodied. If somebody hands you a rifle and you cannot put it against your shoulder and see through the scope, don't shoot it. What happens is people who are small, they have to be the right distance away or you can't see through the scope properly. So they want to like tuck the scope, they want to tuck the gun butt underneath underneath the crook of their arm so they can pull it back and get their eye to see right, but then there's nothing there to slow down the gun, and so the gun comes flying at your head, and the first thing that's there is and if it hits the top part over your eye, you're in good shape because that part of your skull is really, really thick, and so you just get this little half moon that we call an idiot mark. But if your head is in a weird position, then it can drive into your chin. And this cheekbone here is not nearly as strong as that part over the top of your head. That can actually drive the bone into your skull. People have actually been killed by this. So be really careful when you do shoot weapons like this. Make sure that it's securely affixed to your shoulder because when it comes flying back, it shoves your shoulder back, which shoves your whole head back. And so that's why those 3 inches are really important because the gun comes flying back, but doesn't quite hit his face. It comes really close, but by the time it pushes his shoulder back, it shoves his head back, and he ends up not getting that mark on his face. That's why he has a smile. So our first formula again is just M1V1 equals negative M2V2. And of course the negative is the bullet was flying to the right, the gun went flying to the left. And you will see this with all weapons that fire some sort of projectile like that. So, yeah. What fun. Elastic collisions, of course, they bounce. So before the collision, we have 2 objects, and after the collision, we're going to have 2 objects. So again, our total before has to equal our total afterwards, but our total before is 2 objects, and our total afterwards is 2 objects. Now, this is not saying that P1 before equals P1 prime. Because this could be 50 plus 50, and over here it could be 20 plus 80. So the momentum gets shifted around. It's not saying that this is equal to this. It's saying the total of these 2 equals the total of those 2. That makes sense? Now, since P equals MV, then P1 would turn into M1V1, and P2 would be M2V2. And P1 prime would be
M1.
M1 V1 prime, and P2 would be M2 V2 prime. Now, how come only the V gets a prime and not the M?
Because the mass.
Because again, the mass doesn't change. When Julie hits that tennis ball with the tennis racket, suddenly the tennis ball doesn't lose weight and the tennis racket gained weight. The weight stayed the same, the mass stayed the same. What changed was their velocity. So that's beautiful. And this formula would be great, except it really doesn't help us to predict as well as the other one did. Because the other one, I can figure out what it's going to be, but here, I have to know what is happening before the collision, and I have to know what the speed of one of these is after the collision. So it would be even cooler if we had something that was different. So we do have that. So instead of having to know what one of the final velocities is, we can develop a better formula, but this one deals with both the conservation of momentum and the conservation of kinetic energy. So kinetic energy is only conserved if we have a perfectly elastic collision, and we don't know anything about kinetic energy yet. We won't learn that for another couple of weeks. So for right now, I won't show you how we got this equation. I will just show you the beautiful equations. Aren't they pretty?
Yes.
So these are written down for you already, right?
Yes.
Which is nice because that's a lot to copy down without messing up somewhere. But if we look at this, we should be able to predict some things from this. Now, the first thing that we should be able to predict is we have a V2 and we have a V1. So if our V1 is what's happening before the collision of the first object, but a lot of times the first object comes along and smacks into a second object that's not moving, like if we take Bob out bowling. He's going to have all of the momentum is going to be in him, and he's going to smack the pin who's just sitting there unsuspecting. And he comes along and smacks it. So if V2 is 0, then what's going to happen?
Then M1, M2 V0.
Yeah, because 2 M2 V2, if it's 2 M2 0, then this would be 0, which means this whole thing would be 0. Same thing on the bottom section. If we have M2 minus M1 times V2, if V2 is 0, then this whole thing is 0, which means if the second object is not moving coming into the collision, then this whole part is just going to drop off, and all we have to do is deal with the left side of the equation, which makes it much, much simpler. So a lot of times we like that sort of thing. So that's what would happen. That's what would happen if we were out bowling. So we would find the first equation would tell us how fast is Bob going after the collision, and the second one would say how fast is the pin going. Now, when we look at these equations, though, we can be able to predict. So let's pretend that we are talking about the bowling ball and the bowling pin. Here, if M1 is much bigger than M2, because M1 is going to be the one that was traveling first, the V1 is going to go with M1. So this M1 would be Bob and M2 would be a pin. Well, Bob's a whole lot bigger than the pin. So did this get much smaller? No. And did this get much bigger when we added in the pin? No. Which means V1 prime is going to be almost as much as V1. If you have something really big hitting something really small, the first one says, hey, look, that doesn't get much smaller on top and it doesn't get much bigger on the bottom, so it's V1 prime is going to be just a little bit smaller than V1, which means Bob's not going to slow down very much. Anybody ever been bowling before? Yeah, when the bowling ball hits the bowling pin, does it slow down much? No, so we see that's true. Now, if you look at the bottom part, again, if the pin is very small, here we have 2 M1 times V1. On the bottom, we have M1 plus M2. Now, if M1 and M2 were the same mass, then 2 M1 on the top would be the same as M1 plus M2 on the bottom. But here, M1 is much bigger than M2, so the bottom didn't get much bigger, but the top doubled, which means V2 is going to come out almost twice as fast as V1 comes in. So again, if you're bowling and you just hit that one pin, you're picking up your spare. If you hit that one pin nice and solid, that one pin flies off almost twice as fast as the bowling ball came in, which should also match reality if you've ever been bowling. That kind of flies that way. On the other hand, what if the masses are identical? Like when you're playing pool. when you play pool and you hit a nice straight shot, what happens is if M1 and M2 are the exact same size, then M1 minus M2 is 0, which means the first one is going to stop. On the other hand, if we get to the bottom equation, if M1 and M2 are the same size, then M1 plus M2 is the same thing as 2M1, which means V2 prime is going to come out just as fast as V1 came in. Which, again, if you've played pool before, you know if you hit a nice straight shot, the cue ball stops and the other ball takes off just as fast as the cue ball was coming in. So you get that perfect momentum shift where everything gets transferred over to the other ball. Of course, if you hit an angle, it's different, but we'll learn about that on Wednesday. Any questions there?
No.
All confusing. Now, the nice part about this equation is those of you who hate algebra, you never, ever, ever algebra this equation for anything. Yeah, it would be a little more complicated if you had to, but yeah, the good news is all you have to do is blindly plug in. So the only thing you have to remember is, you know, V1 goes with M1. It should kind of make sense that V1 goes with M1 and V2 goes with M2. So V1 is the velocity of the first mass and V2 is the velocity of the second mass. Beyond that, you just got to keep track of directions. Our third type of collision is inelastic collisions, and again, in these they're going to stick together, so we start off the thing with two objects, but we end up with only one because they're stuck together. So again, our P has to equal our P prime. So before we start off with 2, and then we end up with only 1. So again, since P equals MV, P1 is going to be M1 V1, P2 is going to be M2 V2, and P prime, of course, is going to have some V prime velocity, but what is its mass going to be? It's going to be what? Yeah, both objects together. How do we mathematically say both objects together? We add them. So we're just going to have M1 and M2 added together because once they're stuck together, then they're going to be better like that. So most of the time with this equation, what we're looking for is V prime. So everything in the parentheses would just move underneath the left side of the other equation. So that's the worst algebra we have to do with that one most of the time. And so that's basically it. Again, the thing to look for is that direction is going to be very, very important. And so if somebody hits you from behind, then we call everybody positive. But if we have head-on collisions, we're going to call one positive and we're going to call one negative. Anytime we bounce off something and it says it goes backwards, and it has the opposite of what it used to was. So if I was originally going negative and I bounce backwards, I'm now going positive. If I was going positive originally and I bounced backwards, I'm now going negative. So you have to just think, okay, I'm the opposite of what I used to was, and so that's the way that's going to work. So we're going to try this. Bob is rolling toward a pin. Elastic or inelastic?
Inelastic.
Are they going to bounce or stick together? They bounce. If they bounce, that's elastic. So if we have elastic, again, these are the longer formulas, but we're only going to use the left side because initially the pin is just sitting there. So please plug these in. Try it on the calculator.
Because I know you like chocolate.
So see if you can figure out the right spot to stick everything. Ideally, if you wrote everything down in the correct spot, those would be the numbers that you had. If you were able to identify those, that was pretty good. And again, it's not too hard. The first mass you see, the first kilograms that you see, we're going to call that M1. Second time we see kilograms, we're going to call that M2. The only trick is to make sure that the velocity goes with the correct mass. Now, some people freak out because they see, hey, this 7.22 is really close to the 0.909, so maybe they go together. You have to read. So here it says Bob is rolling toward the pin at 7.22. So this is the velocity of Bob. Since he was M1, then this is our V1. And of course, the pin was just sitting there if you stop and think about bowling. So you'd say, hey, V2 has to be 0. If you got confused, that would be why you got confused. So having plugged that in correctly, what did you get for the top one?
5.31.
No way. I got 5.31. So he was going 7.22. He slowed down to 5.31. Did it slow down much? No, because he was really big. The pin, on the other hand, sped up to? I got 12.5. That's what you got? Yeah. That's fantastic. So again, 12.5, you know, that is at double the 7, almost. And again, you know, it's not a tiny mass compared to the ball, but it's small in comparison to the ball. So you're going to get about twice as fast. So that's all you got to do for that kind. It's super duper simple. We love this stuff. So S total, baby. Here we have a 34,500 kilogram semi going 27.3 meters per second, bearing down on an 1896 kilogram Suburban going 29.4 meters per second. They collide, sticking together in a tangled mess. At what speed is the wreckage traveling? So here we say, which formula type are we going to have to use here? The key words are sticking together. That sounds inelastic. Now, directions. Are these going the same direction or opposite direction?
Same. Oh, to begin with?
Most of the time I make this really obvious, but this time I didn't make it as obvious just because I'm here to help you through this. So. Can you figure it out by the way it's red? Okay, if you're bearing down on somebody, that means you're getting closer to them, right? But can you bear down from behind or bear down from in front? Yeah, you can. That just means we're getting closer. So I know I'm getting closer. Can you tell if I was coming from behind or if I hit head on?
From behind the line, because bearing down.
When they hit from because of the velocity.
It has to be head on.
Yeah.
Because when you look at it, the Suburban is going, no, the Semi's going 27, but the Suburban's going 29. If the truck crunches into the Suburban and he's going slower, could he be hitting it from behind?
No.
That would be kind of hard. So the only way this is going to work is if they're going in opposite direction. So the formula type says, yeah, this is my inelastic collision. And I'm going to be looking for what? The V prime. So if I'm looking for the V prime, then everything in the parentheses is going to go just underneath. And it would end up looking all pretty like that. So what are we going to call M1? The 34,500. And the V1 is going to be 27.3. The 18.96 will be M2. And what is V2 going to be? Not 29.4. Negative 29.4. Why does it have to be negative? Because he's going in the opposite direction. That'll make a big difference in our answer here. So we will end up with that mess. And again, do the whole top part, hit equals before you do that bottom. Or else use fraction mode on your calculator, whichever one you like better. don't have fraction mode on your calculator, it's better to actually have parentheses around the entire part of the top, or like I said, hit equals before you hit the divided by part. And plugging all that mess in, I got 24.3 meters per second. Anybody else get that? Good. Now, here's a very important thing. These are really realistic numbers. This is the actual mass of the semi. That's the actual mass of the Suburban. These are both going highway speeds. We deal with a lot of 18-wheelers here, so this is a good thing to know. This is realistic facts. Look at the change in velocity here. The Suburban was originally going 27.3 after smacking head-on into, the 18-wheeler was going 27.3 after smacking into a Suburban head-on. He slowed all the way down to 24.3. That's a change in velocity of 3 meters per second. Would he have to be wearing his inertial restraint? No. Would he even spill his coffee at that speed? Boom. 3 meters per second slower. He'd practically not even know it happened. On the other hand, if we look at the Suburban used to be going negative 29.4, and immediately after the collision, he's going positive 24.3. That is a delta V of 53.7 meters per second. So that's the equivalent of you going almost 200 miles an hour and then slamming into a bridge or something. So who always wins in these wrecks? The semi. So what I'm saying is don't be paranoid around these guys, but do treat them with respect. Now, I drive around these all the time, and what I see is that for every bad 18-wheeler driver I see driving crazy around passenger cars, I see about 500 crazy passenger cars driving around the semis like, oh, they're so annoying, which I know they are, but you can't just jump in front of them and slam on your brakes and do stupid things like that, because if they have a hard time speeding up, they also have a hard time slowing down. And people just don't treat them with the respect that they need. So be real careful around doing foolish driving things around these guys, because you're going to lose really, really bad in a wreck with these guys. In fact, I had a challenge for many years that I would give somebody a free A if they could find me an article that involved a passenger vehicle and an 18-wheeler in a collision where the 18-wheeler driver got hurt. And it went on for years and years and years, and we could never find one. The closest we got was one time a guy was trying so hard to avoid a wreck that he ended up flipping the rig over, and even then he didn't get hurt. So, yeah. So you do want to be really, really careful. For homework, of course, we want to do problems being. But first, I would like to show you a little video clip. And this little video clip is one of those clips that one of my old students sent to me one year, because he said, hey, this reminds me of when you were talking about 18-wheelers and people driving in class. So here's a kid that decided he was going to steal a riding lawnmower from someplace and stick it in the back of his truck and then run from the cops. And so this is being taken by a police camera who's chasing this guy, and he's about to approach an intersection where there's a red light, and, well, you'll see. Yeah, they'll show it again in slow motion here. I want you to look closely at the change in velocity of the 18-wheeler. Okay, there was a little rocking sideways and no substantial change there. Now, obviously, the two people in there were turned into dust instantly, and so they didn't even know what happened. This poor guy in the red car probably had nightmares for years, as did the wheeler driver. So, you do want to be respectful of these things because, yeah, there's not a substantial delta V for that 18-wheeler driver.
I gotta go to therapy.
Yeah, I think so.
Peter, saw it.